Good morning. This is your staff sensei, Mr. Spensei, and we're going to do this is project test or extra credit test A, problems 32 through 40. In a carnival game, a person can win a prize by guessing which of five identical boxes contains the prize. After each guess, if the prize has been won, a new prize is randomly placed in one of the five boxes. If the prize has not been won, the prize is again randomly placed in one of the five boxes. If a person makes four guesses, what's the probability that they wins exactly two times? So in this time, we have four guesses. We want to win twice. So we could have zero wins, one win, two wins, three wins, or four wins. The most we could have is four, but we're only looking for a singular value. And um, we have five boxes, only one of which has a prize. So the probability of winning on any one guess is 1/5, which is the same as saying 0.2. So since we have a fixed number of trials, a fixed probability, then we are looking at a binomial and we're doing four trials. We want two successes. The probability of a success is 2. The probability of failure is 1 minus 0.2, which is 0.8. 4 minus 2 is also 2. So our answer to number 32 happens to be E. Okay. An engineer for the Allied Steel Company has the responsibility of estimating the mean carbon content of a particular day's steel output. Using a random sample of 15 rods from that day's output, the actual population distribution of carbon content is not known to be normal. So we have a random sample of 15, but the graphic displays of the engineer sample result indicate the assumption of normality is not unreasonable. So basically, they did a box plot or some sort of plot to determine that it's not unreasonable. The process is newly developed and there's no historical data on the variability of the process. So they're telling us we don't know what the variation is. So if we don't know the variation, that means we don't know the standard deviation. In estimating this means content, the reason the engineer should use a T confidence interval rather than a Z is because they don't know the variation. Is estimating the mean using the sample mean. We do that all the time. That's the purpose of a confidence interval. Is using the sample variance as an estimate to the population variance. I like this. Let's look to see if they say anything about standard deviation. Because normally we say, hey, if we know the standard deviation of the population, we use a Z. If it's standard deviation of the sample, we use a T. But they're talking about variance, so it's probably B. Using data rather than theory, that doesn't make sense. Is using data? No. Has a small sample? No. So the best case is variance because variance is basically just saying that. So that is why. All right. Number 34. Each of 100 laboratory rats has available both plain water and a mixture of water and caffeine in their cages. After 24 hours, two measures were recorded for each rat: the amount of caffeine the rat consumed, X, and the rat's blood pressure. The correlation between X and Y was 0.428. Which of the following conclusions is justified on the basis of the study? The correlation between X and Y in the population of rats is also 0.428. No, we can say that about laboratory rats, but we can't talk about the population of rats. So maybe that doesn't sound too good, but maybe. If the rats stopped drinking the water caffeine, this would cause a reduction of their blood pressure. We don't know that. We never tested that. We only tested what happens when they drank it with caffeine. About 18% of the variation in the blood pressure can be explained by a linear relationship between blood pressure and caffeine consumed. Ooh. Well, correlation was here. That's R equals 0.428. But variation in X can be explained by a linear relation between them. That is the definition of the coefficient of determination, which is R squared. So let's go ahead and square R and see what happens and see if that is 18%. And so 0.428 squared, sure enough, I get about 18%. So this is my answer because 18% is the coefficient of determination. And coefficient of determination is the amount of variation in y that can be explained by x, by the linear relationship established by x. Number 35. In the test of hypothesis, mean of 100 versus mean greater than 100, the power of the test when mean is 101 would be greatest for which of the following? So basically they're saying, hey, you know what? We should be rejecting because it's not 100. It's definitely greater than 100 because it's actually 101. So we should be rejecting. When are we most likely to reject? Power is increased when? As n goes up, power goes up. As alpha goes up, power goes up. So in this case, we want the largest sample size and the greatest alpha. Largest sample size is 20. Greatest alpha so is 0.05. So 35 happens to be C. 36. An urn contains exactly 3 balls numbered 1, 2, and 3. Random samples of 2 balls are drawn from the urn with replacement. Okay, and then they give us as average. Now, we're drawing with replacement and we're doing it twice. Wow. Okay. Anytime we do something twice, you should be setting up a table. So I've done that. 1, 1, 2, 1, 3, 1, 1, 2. So I set it up. All right. So here's my table. But it says this one plus this one divided by 2. So 1 plus 1 is 2. I divide by 2. So if I sum these up and divide by 2, I get 1. So that's where the ones are coming from. Well, how often did that happen? Well, 1, 2, 3, 4, 5, 6. So 1, 2, 3. 3 by 3 is 9. So this happened 1 out of 9 times. So this looks like this is my answer. Let's jump over here. Well, 3 plus 3 is 6. 6 divided by 2 is 3. So this is equal to 3. And how many times did it happen? It happened 1/9 of the time. So that looks good. So we'll look at this middle row. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. All those end up with 4 divided by 2. And that happened 3 out of 9 times, or 1/3 of the time. So my best answer choice is B. Okay. Anytime you do something twice, it really helps to make a table. A simple random sample procedure produces a mean of X bar of 15. A 95% confidence interval for the corresponding population is 15 plus or minus 3. So that means 12 to 18. So we're 95% confident the true population mean lies between 12 and 18. So we don't talk about measurements. We talk about the mean. 95% sample measurements, again, talking about measures. If 100 samples were taken, 95 would fall between that. No. If all samples were taken, we would expect 95% of them to capture it, but we didn't say that. This is the P for probability, so I don't like that. So it better be this last one. I hope it is. If U equals 19, oh, the true population mean is 19. Well, 19's up here. This X bar would have been unlikely to occur. Yeah, because we're 95% confident that it's here, but if it's 19, then that would fall in the 5% category that we didn't think would happen. So if it's 19, we'd be unlikely to get a sample like this. All right. If it's really 19, that would be unlikely. Sorry about that. Number 38. Suppose that public opinion in a large city is 35% against increasing taxes to support the public school system. All right. If a random sample of 500 people from the city are interviewed, what is the approximate probability that more than 200 of these people will be against increasing taxes? So we want the probability that X is greater than 200. All right. So which of the following setups would answer the question? Well, the problem with these two is this is set up as a binomial, and this is both, and this one is wrong because that's in the wrong spot. But this one is wrong because it doesn't include 201, 202, 203, 204. We would have to include every value above 200, and it doesn't do that. So that's not right. So let's look at the normal. And what we know with the normal in this case, we're centered at 0.35, but we had 200, we got a sample 200 over 500, which is 0.40. So we're looking for the probability that this is greater. But if I were writing my null hypothesis is HO P is 0.35. All right. Since it's a hypothesis statement, we always, so P is 0.35, P hat is 0.40. So we're going to be looking for 0.40 minus 0.35. So that gets rid of this one. Now the question is, which one do we use here? Well, when it's a hypothesis test, we always use the claim. We assume the claim to be true. We don't use P hat. So in this case, we assume the claim to be true, so we use P. All right. As lab partners, Sally and Betty collected data for significance tests. Both calculated the same Z statistic, but Sally found the results were significant alpha equal 0.05, while Betty found that they were not. When checking the results, the women found the only difference in their work was that Sally used a two-sided test. So let's figure out when Sally would have rejected. Well, if it's a two-sided test, that means 0.05 divided by 2 is 0.025. So she could only reject if her z-score was in those tails. So second vars, inverse norm, 0.025. And we'd have a negative 1.96. And we have a positive 1.96. So any value greater than 1.96, we would reject. Well, that's not greater than 1.96, not greater than 1.96, not greater than 1.96. Any value less than negative 1.96, we'd reject. Well, this value is, and it's the only one, so it had to be that value, because negative 1.98 is down here. Let's see, this was Sally. But Betty, and this is confusing, failed to reject. And she also got a negative 1.98, but she failed to reject. But she did a one-sided test. Clearly, if she had been down here, she would have rejected. But if she'd had it greater than second vars inverse norm of 0.05, if she'd had a negative 1.645 and had turned it this way, a less than, she would have rejected. But if she had a greater than and shaded this way, she would have failed to reject. She would have needed a 1.645 or more to reject. So Sally rejected because it was a negative 1.98. Number 40, a student working on a history project decided to find a 95% confidence interval for the difference in the mean age as the time of election to office for former American presidents versus former British prime ministers. The student found the ages of the time of election to office for the members of both groups, which included all of the American presidents and all of the British prime ministers, and used a calculator to find a 95% confidence interval based on the t distribution. This procedure is not appropriate in context because the word all tells us they did a census. And if you perform a census, you do not need any statistical measures. because the entire population was known and you know the actual values. So the entire population was measured in both cases, so the actual differences can be mean with, and a confidence level interval should not be used. Once again, if you no statistical methods are necessary if you conduct a census. Thank you for watching. Hope that helped. See you in the next videos.